This work made with all these collaborators here, and not including the work that Raul mentioned yesterday. I think we had enough about that. So, I mean, this is independent work from that, but in the same spirit. So this talk will have different parts. So just so you don't lose what's going on. So the first part is only basically LSS. There's no gravitational wave at all, right? It's just a new methodology that I want to share you, and please interrupt me for questions. The second half, I'm going to discuss about stuff that cannot be velocities, which include gravitational waves, but also supernovae. And then I will pull a Ricardo, and then the third half of my talk, I will talk about gravitational wave science. So let's see how it goes, right? So there are two methods in this talk, right? So the idea is that you can use standard candles to improve precision LSS, not only as a distance indicator. This is what I want to say. And then the second is this new methodology, which we have named free power, that try to analyze the elastic structure without any assumptions on the early universe or on the dark energy model. So trying to be more robust, even if sacrifice a bit of precision. Okay. The idea is that in times of tensions, accuracy is somehow more desirable than precision, in my view. So this is part one. This is the free power methodology. And okay, I'm not going to spend much time. You've seen this many times probably over. So yeah, I'm not going to discuss much the tensions, right? But sometimes the tensions are discussed as an early versus late time universe tension, both for H0 and sigma 8. It's not exactly that clear cut, but the idea is that I want to have a late time universe analysis, which is no information whatsoever from the early universe. So that's the goal, okay? So here, for instance, this is the SBAO results. They do have these results. We might consider maybe they are independent from the early universe, but not completely. Either you have BBN, or you have the star, which is the position of the peaks of the CME, or you have RD, which is the sun horizon at the last cabinet. So these things are all early universe in a way. So if you have your preferred early dark energy model, these things change in principle, right? So the point is, can you get LSS constraints that use no information from BBN, no information from the CMB whatsoever, and even not even these quantities, which I agree are more model independent, just the peak of the CMB scales for RD. It's not using the full shape of the Planck spectrum, but can we even avoid those, right? And of course, I will not be here if I didn't think the answer was yes. And the ideas that I want to show is that you have a fundamental scale in the fields, which is independent of the BAO scale, independent of the turnover scale, and you can measure this by combining just two effects, the Alport-Krasinski effect and the redshift space distortions. So a brief summary for those who are not familiar, the redshift space distortion is just a method that is a clear consequence of the fact that if you have a sphere in real space and you have an overdensity, in the universe, the rich always gets richer, the poor always get poorer, right? The concentration is always increasing. So this, if it's an overdensity, will collapse to keep increasing. So it means that if you are here on the bottom of the screen looking up, objects which are closer to you would actually be moving away from you, and objects which are farther from you are moving your other direction. So a sphere in real space looks like an ellipsoid in redshift space at linear orders. This is the 1 plus beta mu squared, if you want, effect, right? On the spectrum is squared. Right, so this will show up. So this mu is the angle between the Fourier mode k vector, unit vector, and the direction you're observing. So it's a modulation on the direction you're observing by the Fourier vector. Okay, this is well known. This is used analysis, as is Alport-Krasinski current analysis, which is just saying to you that if you have a wrong model of your background, then spheres can be mapped into ellipsoids just because you're assuming a wrong homogeneity, because what you have today is angles and fluxes, and you convert that into fancy things like distances, right? And these things assumes a cosmology. So whenever you go from angle to distance, even a simple thing as saying what's the cable, there's a lambda there, so there's a distance implied. So you can map spheres into ellipsoids or even spheres into larger or smaller spheres, okay? So if you didn't think about this, especially for the students, I'm not going to explain this in more detail, but think about this carefully. Now, of course, if you are on small scales, then you have no linear effects. The velocity becomes larger, and you're going to have a no linear scatter. So this is the collapse, but if you visualize that in the center there, they'll be scattered. And then this means that the very center of the object will actually be elongated on the opposite direction, okay, perpendicular direction. So this is the fingers of God effect or nonlinear space distortion. Very good. So you have both of them combined. This has been known for and analyzed for 20 years now. Now, of course, the simplest thing you can do in LSS, I think, is the video scale, right? Just either the wiggles of your power spectrum or the population function of the excess peak around 150 megaparsec, combining all the galaxies you're observing, okay? And it's assumed to be more robust to small scale physics because it's just one simple scale. Now, for a long time, people have been pushing this another analysis, which is called the full shape analysis sometimes. That's just put out the full shape paper last month, which is, okay, I don't use only the position of the things, but it's the full shape of the power spectrum, which has much more information up to some scale in which I trust my theory, right? So if we go from some K-mean, which is dominated by window, K-max, which is dominated by universal theory, and you often see, especially in theory papers, people say, well, linear can go to 0.1, and we're discussing last week, the loop expansion maybe you can go to K of 0.3, right? And if you're doing fancy things, like Mateo was saying, maybe you can push to 0.6 or 0.7, right? Be great. So one of the things I want to see is that if I can do what Mateo was saying in this method, it would be fantastic. Let's see. Now, of course, if you want to go to 0.1 even or further, you need to do some pure linear theory. So EFT of the LSS, effective theory of the LSS is what's being pushed a lot. And but what I want to say is that whenever you have a shape of your power spectrum, you're assuming some cosmology in the universe. You're using a Boltzmann code. Of course, you're using Campbell class, right? And you're assuming something for the W1. That's why, if you look at this paper, there's the results for WCDM, the results for WCDM, they're different. So you're assuming both background and perturbation parameters. Now, this method I'm trying to propose tries to be fully modern and not having these caveats. And the idea is quite simple, actually. You, instead of, say, omega meta, W0, WA, you don't use those parameters. There is no omega. That is a constraint, model constraint, okay? If you realize this, you say, okay, what can I do? So I'm saying that I'm going to just take my linear power spectrum and just pin them in k-bits. Okay, so I'm not doing here harmonic space. We can try to do this in harmonic space, but let's do like Raul did, take the block and hit it into the cylinder hole. And okay, it's power spectrum. I pin it in k-bits, and those are free parameters for me. They're going to be free. For that. And I have a growth rate, which can be either scale dependent or scale independent. You'll understand is scale independent. Right? The linear growth, sorry. But if some modified gravity model, there is a scale dependent, but usually it's only dependent on scales. Okay? So even many modified gravity models is almost constant in the regime you want. But you can do that's your choice. And you do not use a Boltzmann code at all. You just use a Cock-Pachitsky and space distortion to put modern dependent constraints. So if you're not using a Boltzmann code, you're not using the early universal way. Okay, that's the point. So how does this work? Is because because of Cock-Pachitsky, your mu actually goes to mu prime. So you only the mu when you're doing a theory, if you're assuming some distance, you can assume CDM as a reference model to convert angles in the sky to distances, and then you get k vectors. And you get this mu vector, so the mu angle. And then if you are in the wrong cosmology, because you thought it was not CDM, but actually it was AW not CDM, then you have a different mu. And when you go to mu prime, you change your multiple structure. There's a monopole particle accident for everyone discussing about. And this dependence is fundamental. It doesn't come from a particular theory. It's the same in different energy models, different models, the multiple points of the structure. But if you're in a raw cosmology, you change the structure. You gain L equals 6, L equals 8, L equals 10 in principle. So you can say, well, the right cosmology that does not have L equals 6, L equals 8, L equals 10, apart from observational problems, okay? But more than this, the ratio between monopole, parapole, also is given by the theory. So you can say the right cosmology that gives the right ratio of these multiples. So these are these are the actual formula they enter. So you have a reference mu, and what you observe is this mu, and this R index is the reference cosmology that you have to use. So they have HR and the I. So this parameter distance. This is the Hubble parameter, that's Z. So whenever I have direct cosmology because I was lucky, the H equal HR, D equal DR is cancelled, and you get mu equal mu1. And the same for K. K will be only DR if you have the right distance and Hubble. Someone was asking something. Who said this?
Io lo sei, non so, so kind of runway or split case.
Right. So I will do both. So I will show results only using linear theory, which has no redshift result. The result which you just put analysis parameter like a simple model, like extra Gaussian, which an access scatter. And then I do one loop. And then the one loop, there are different East Coast, West Coast parameterization where either you put them as an extra analysis parameter or you take into account by the counter term of the theory. So there is a discussion. So we did try over a few papers, different things, and there was changes a bit here and there. You're right, but yeah, you have to worry about this.
Then if you were ready to do a Kropatschinski, that is basically the same as the standard Kropatschinski method, right? Because
That's it. Yes. So
using that one, they materialize over the world one, which I assume which is the same of materializing over the
and so the observable is there, right? The observable is not new. It's just the way to analyze it. Then I'm gonna say that I'm not putting cosmology anywhere, but the observable opportunity is there. So there's parallel perpendicular scale in this case. Maybe this is a super question.
No, yeah. I guess it's really going to be the knowledge of RSDs, but that is just some very green power series in KU squared. So if you're just eating basically three terms in every single one of these.
Right. So in this, right. So that's the problem that we have to truncate the series somewhere, right? And this is still, let's say, up to debate how we do that, right? I don't have the answer because we haven't investigated all possibilities, but yes. So even the two loop, you have to assume the two loop is not there. You can do some testing, you can do some simulation, some mocks, then to see if the two loop is not there. And there are some parameters which are completely degenerate that I fix here. There's one parameter I fix, but in the end, I'm going to have 7 bias those parameters in this analysis, but this can be revised. No. So I'm saying I want to show 2 results. One only using linear theory. That's only being one. Another one using one loop, and then I'm going to have 7 parameters.
Okay, but that's the for the shape. Yeah, 3BO shape and 3 power. What you're going 3 power and 3 more.
No, in 3 power, I'm going to use the effective theory as well. Why it's not full shape?
Yeah.
Because my variables are now the linear power spectrum instead of omega beta WA W naught. That's the idea. So H and DA are going to be frame variables in my parameters. So it's not a complete breakthrough. It's just a new way of looking at the data, try to separate really what is, model event.
Yeah. So basically, what you're saying is that what you're calling full shape is if you assume some fixed form for the power spectrum, either a power law like and or the linear prediction.
Yeah.
Where you're saying instead is that there's just like kind of pieces of like voxels that you're just assuming the flow independently.
Yeah, the linear effect is equal 0 is independent.
Right.
And each Z I can just use the growth rate and growth function to get there.
And is there some prior on like monotonicity or smoothness or anything like that between the?
No, I'm not using. I'm not using it, but so I'll get to that. Let's see.
Can't type it check again. Why should let's say division? Why should it be here?
Why do I keep being linear figure? Yes, because I'm saying the Kropatschinski, I just want to measure ratios between monopole, quadrupole, and different K-means. And I want to measure if there's equal 6, equal 8, equal 10, something like this. So these are the direct concept. It's the closest thing to observe the closest theory I have to the observer. I want to be as close to the data as possible. Okay, so the point is, I'm going to show you can constrain all these 3 quantities here. They're dimensionless Hubble, the dimensionless distance, and the F, which can be scale dependent or scale independent, your choice. Now, as the derivative of the basic context, right? So the growth rate. What I point is that there are few observables that give it directly H. Right? You can do radio VAO, of course, but radio VAO has a RD or RS or radian change notation. So you need to understand what is this guy. You have redshift drift, which is a morphotronistic thing you can do with the ELT 40-meter telescope or 10-meter telescope, which is just the equations, and observe the redshift, and wait 10 years, observe again, and there will be a difference on the 7th decimal plate. And that gives you direct information of H of C and that C. And that's been proposed, but it takes 2 decades. But we'll get there. And there are nice things about this, because if you think about 100 years from now, this thing will become very powerful very quickly. But then cosmic chronometers is being, you see a lot of papers with cosmic chronometers these days, but they rely, and I'm not an expert on this, but they rely on astrophysical modeling of passive galaxies. You have to know a bit about that, and something about the population synthesis. So these are up to debate as well. Okay. Now I'm going to show you a few forecasts that I have done with this, and it breaks a bit the causality of the top. But this is, I'm going to use supernovae only as tracers of that method, which is part 2. Right? Just LSST supernovae now as tracers, tracing the density field and tracing also the velocity fields. Okay, I'm going to explain this more detail, but using this free power method, because this is the first time we thought about using this free power method. And a lot of supernovae, okay, LSST after 10 years, so five years of LSST, and we should get constraints in like 5, at least here, I believe. These are more speculative, but here at LSST we have lots of supernovae. 5 to 10% constraints rate of seeing all the speeds, which are independent from cosmology. And sorry, and these are my free. See, I have these are the for different redshift beams. I'm putting here different binning options, and I measure P linear. So this is given by directly. There are 3 variables that I fit. Yeah, questions here. Go on. No. This is a forecast for LSST. This is more than 100. Yeah, no. So this is oversimplification. Okay, but just showing that if you have a couple of 100,000 supernovae more or less, you can do these things. All right, now how to get there? This is part of a different talk. I'm just showing here as a part of the free power method. And with my student Camilo, we are analyzing Pantheon Plus data and SCF5 data for this. But I'm not showing any results here. Have to use the USME for that, right? It has to be a typo correction for that. That'll be the second part of the talk with me, because also I better to load a bit of the question.
So you showed the EDK right, but you mentioned it 3 times.
Yeah. So this is not the 3 times to point maybe you're used to. This is a different 3 times to point. Okay, this is density and velocity power spectrum combined, which is also a different 3 times to point. There's no lazy. Let's go on. Sorry, yeah, this slide is a bit out of place. It's too many things there. Yeah. You are right. So there's no EFT. We discussed this a bit, but if you go to one loop, it's much less. It would say you get many new spectrums of unique. You get several bias parameters, a few counter terms, and you have to marginalize over them. And that's the point. Is that what's the progress for these things? Right? The theory does not actually give you model dependent price for these guys. So the idea is that I would like to have them all uninvolved. Like infinite price, and I'm going to get results. If I can do that, I'm doing okay. So this galaxy gas power spectrum, so those are so familiar. So you have a linear part everyone knows about. You have the one loop corrections, you have ultraviolet corrections, and you have a short noise correction. And you have here maybe or maybe not a non-linear RSD part, which you can add. Okay, you can add either here or put it into the preview terms. That's what I was saying. The linear part has this kernel here, which is just nice way of writing 1 plus beta mu squared plus a growth function and the linear power spectrum. The one loop part, we have a P13 and P22. This is delta Q. This is delta squared. These are the components there. And all of this involves different integrals in momentum space, which I'm not going to show here. So now on a second forecast, now there's no supernova here. I'm going back to galaxies, only galaxies going to one loop with uniformity frac. So we wanted to see if I put uniformity fracs and marginalize over them, do I still get something? So the results are the thick lines. They are different redshift beats. And this is eta. So eta is the Sapolsky parameter, which is the combination of H and D, which is what is easier to measure. this combination, okay? And what I'm showing here is up to some k max. Since this simulation can go wherever I want. Stopping at 0.25 reference, and saying that how he gets information. So this is what I was asking Matteo about, and asking a lot, because this guy here, the error bar goes down fast with k. So if you are at 0.2 or 0.4, it's a huge difference. Why? Because usually people say that doesn't matter much, but then think about omega m. But there's no omega m. Right? But the multiples are there all the time. And the higher k max you have, the more modes you have to measure multiples. See? So this goes fast.
It's just omega m. I think you can measure V1 better.
Yeah. I'm oversimplifying, yes. Of course, yeah, you're right. But I'm saying, but this goes very fast, more than usual. And in dash line, I did this nice exercise. I think it's nice, maybe long. So it's the linear, this is only the linear. So I stop at the linear power spectrum. I don't include any more loop terms. And then, of course, at each given k, I gain a lot because I have many less parameters. But what I think this is telling you is that you are artificially getting a lot more results. Because what you're doing here, you can think of, I have 6 parameters which I put delta Dirac priors. So unless you can convince me of those delta Dirac priors, you should be there. I don't know if it's clear. So I have to be careful. So I don't even know the true loop here where it's going to enter, right? It's one of the open questions. And you can get even more if you have the P spectrum, because the P spectrum has lots of modes, but it shares many of the same bias parameters. So I share the same break loss of the genetics by including the bias spectrum. So here I'm just showing the error using the power spectrum over the error using both power spectrum and bias spectrum for different parameters. And it's how much I gain. So for the growth rate, I gain a factor as much as 5, depending on redshift. If I put the bias spectrum, it's a lot. For the H and D, I gain a factor of 2, which is nothing clear about, even though the bias spectrum is much messier, right? Which involves much more manpower to do this. And 3, this is how I compare to different observers, right? So this is just to this is doing DESI and sorry, this is Euclid forecast. This is Euclid forecasts. Euclid like, and then I have 2 aggressive conservative. Forget about that. And this is what we get from cosmic chronometers. So you can be much more competitive than cosmic chronometers with much less assumptions. And this is what I get for distances. Now, distance at redshift 2. Of course, you can put supernovae here. Supernovae will be better. But then supernovae is a very non-linear, dirty thing too. No, I like it, but you have to know it's dirty. So, and I compared them with LISA science. So LISA is not really targeted to do bright science. I can get that, but we can do better than LISA. So it's nice. So I'm gonna just say a second that what we measure, right? So I think I can spend a few seconds here. So usually what we measure in normal BO analysis, you can measure this quantity, H times D. That you can do BO. Right? You take the radial BO and the transverse BO and combine them, you can get this quantity without RT. You can do that. But you cannot separate H and D. And instead of H and D, I'm going to use E and LA, which is these dimensionless quantities, because this method cannot measure H naught. I say that up front, so don't get excited. It can measure sigma, but not H naught. But I only measure this. You can understand why it's only angles. It's all dimensionless things, right? You see. Anyway, so these are related to this PAO parameters, H parallel and H perpendicular. Okay, but again, I remind you that in the normal BO analysis, you have an RD here free. Okay, so you only measure the A over RD or the H over RD. You can measure the A over the H that you can do, but you cannot separate the A and the H. The clean. Okay. Now, on free power, you can measure the combination, but you can also separate them. So you can see, I think. So the reason that this LA quantity dimensionless distance is the generally this point is the linear power spectrum. So if you're only the linear part, you cannot separate them, just as you did. Okay, I'm outside of that. But, so I'm actually going to skip through this. This is the condition, but I'm just you can show the question. You can come back to this. But you cannot, and the linear part, you can show that you cannot break. So only by going to linear can you break the degeneracy between T, sorry, LA and E if you want. We have to go on. And this is similar, I'm going to call it here, similar to what happens in the Fouché balance, that in the linear you only measure F sigma 8. But going to here, you can read the chance and measure F sigma 8 separately. Here, I can do that as well, but I can also break the difference between H and T. Okay, another thing, the power spectrum in the real world has wiggles, but this method would work even if the real world had no wiggles. It doesn't assume even wiggles to be there. Okay, so if you have a wiggle other than a wiggle, you will change the precision. So you get a bit tighter constraints if there are wiggles in the real world, then there are. But the accuracy should be robust. And I was saying, if the difference between LA and E is only broken to nonlinearities, because what the metric speaking of is a fundamental scale on the power spectrum, which is the scale of nonlinearity. So that's the thing I want you to know, to absorb. There's a scale of nonlinearity, which is not dependent on making a model for dark energy or making a model for the universe. It's just gravity. Gravity will introduce nonlinearity.
Here you mean nonlinearity of the matter force?
Yes.
Or the galaxy force?
Well, there's no end to the net power spectrum, which is there, although it's kind of hidden with all these parameters, right? But it's there. So you're trying to pick them apart. So this is like a tradition exercise. 3 power spectrum, this is scale and speed. So the number one is with wiggles. The dash one is without wiggles. And the blue line is a power law power spectrum. Okay. So when I have a red, I get these results, and these are different K mass. And this is measuring either L and H separately. This is the L and H, this dimension, or just L. So when I'm in the scales here, I don't bring the degeneracy. I measure the combination, but I don't measure the vector here. This is fixated, so that goes to infinity. But the yellow is not measured, it's degenerate. And as I go to nonlinear scales, I break the degeneracy and measure them similar way. When I don't have wiggles, I also break the degeneracy. But the constraints become a little bit worse if you look them together. But if I have a group of a spectrum, I never break the degeneracy, they never converge. Okay, so you can show this from fundamental principles. You can pen and paper, you can show these things. So it's nice to see this work. So this was all Fisher matrix, okay, analysis. Fourth thing is that if you can have E and LA separately, then you can do something which is not trivial to do, which is combine them to get the curvature. So you can get spatial curvature in this model dependent way. Because this relation here of the curvature, this is the derivative of LA spectrum C, this is the double expansion, this is LA squared. This only assumes freedom of all Kantians. This is always true. Unless you are in the like Thiago. Right. So the Thiago can help me get a form of that for Milan or else. But anyway, you get this guy, right? And you can measure these different beats. So in each beat, you can measure omega k. You can measure omega k at each beat. Of course, omega k is a parameter today, but you can measure that in 8 measures once. Okay. So you can do this. We did a very simple proof of concept to finite difference, nothing fancy to get this delivered. It's smart. And that's what we can do for this is that's and liquid combined. That's it. One and liquid combined. So I'm showing you all 3 pressure beats, but you can do that with many pressure beats. And you can combine them. And this is the posterior the curvature for different beats, and they combine what is the breadth. Okay. So you can measure curvature to around 5%. Those assumptions, which is honestly most of the designs. If you have a quantum price limit, you can go to 3%. Or of course, you can, if you put your higher C, maybe as well. Which is comparable to what we get in LSTM. These are maybe lots of assumptions about the model. So this is, sorry, this is assuming LSTM, right? So not really the 3 power thing.
So like, that's the idea, and we push you should be able.
This is Fouché. Same thing, max, but
Yeah, it's more the information to know from the right? Okay.
yeah, I think so. Right. So, how do you measure the loop spectrum? In case you have a condition free. Well, the integrals of the beam. Yeah, so then, yes, right. So either you smooth them out, as people saying, doing some, you can do polynomial fits to the beam, or you have to think of some. We are doing squared polynomial loss fits. That's what we choose to do. So we fit a polynomial, but then the more beams you have, the less this is sensitive to what you choose. Right? Yeah, that's a feature, right? So you don't have to do it. I mean, you can do it a few times, but yeah, for them, so yeah, that's totally LSC. So this is the result we did for boss data. 2 bits. We assume after we developed only 8 bits because this was you know, an identity for SFC. I was not a super expert on this. But 100x.3. Okay, they completely default primes. They count the primes. So the primes are as wide as they need to be. So it was a challenging converting assembly parameters, and I know people here do the parameters, but it was, I was just finding, I thought EMC would help me out, no way. Right. But you know, under KCPU hours, that's the end, what we use.
But it is like KBs for the
No, so I have to go, okay, so there's something there. To uncomputed loop integrals, I have to go beyond K-3. Right. So I have to go, I look until K equal 1, but I only use all my likelihood of the 3. So I computed that I separated 1, computed the envelope, but then I separated.
so you have 8 parameters that are in the overnight
8
but between the 8 and the 17.
Yeah, because this is 8 only the and I have minus 7 minus 100. I have F, H, and D to 3. 8 with about 11, and I have 6 bias parameters. So 6 free bias parameters, P1, P2, P2, PNF, and the rest of the if you understand C nodes, yes.
Where you can know the shape from one head to the next, but just then you could be tabulating all of them in the rule immediately because all you did, and it's only we should exactly so
Yeah, so the likelihood here is taking only 2 seconds. It's not so bad. If I burn this code, which is not well, 2 seconds. The problem is that the conversion DMC now I solved this problem. It's much faster now. I no longer it's so challenging anymore. Because to get here was challenging. Now it's okay. But yeah, you can do lots of tricks. You're right. That it's facilitated on the guys to know. So I'm gonna go faster just to say because I'm using this fine logic data set. That's my data. Okay? The trees with the window functions, the wide angle transformations, and it's just the blocking, right? The cow trying to forgot the name, trying to resolve the POP better. Anyway, let's get the results. So this was actually done in collaboration with this master student in Germany when I was there in mathematical. So this is the results for the low pressure P, and the second parameters showing in line 7 here. The important ones are E, LA, and F. So the point is things get somewhere. You get constraints, even though for these parameters the primes are broader than what you see here. The orange is the LCM results. And this line here is what you get. This is the best in the blood, and this is what you get if you change megamet. So megamet is 0, is 0, megamet is 1 there. If you assume LSM for a second, you don't have to. So this is just only this is a sigma expansion. Okay, seriously, 2 sigma. Okay, if you want this favorite low megamet, but again, there's no megamet. Very good. So this is the low Z, this is the high Z result. You have a preference for a little bit larger distances. And a little bit again lower Hubble parameter, the growth construction F is more or less what you expect. Right? There's some people that like this here. Where we'll see the W numbers here. W numbers here. If W numbers are in the same place. It depends on that. They do a law line that they check that. You check the number. You can improve this a lot if you add some prime on the distances, because you can say, wow, okay, but I can measure distance with binary stars, supernovae. So this is not using particular supernovae data set. This is just representative of what we have today for supernovae. So this, if you take 15 supernovae direction P, which we have, and do the constraint at 3% error in distance, and then the rule becomes a red. So you can constrain much better if you want to use this analysis with combined with supernovae. I'm going to plan to do that in the paper. And this is going to direction P. So it doesn't change too much for the bias parameters, but a bit because they are related. But for the distance, a lot, of course. And for the E as well, because they are. You can measure F directly. So This is the result of equals conversion. This is from the paper by Ivanov, Simonovich, and Sologate, which they do a one loop expression by lofty power, and I go to the bracket in a different power. So I use a factor of 2 to quantify the precision, which is expected because I'm doing much less assumptions. But I can put no. I mean, for plot there, which is only going to improve with density. Okay. So I this is a good trade-off. And we have our primes are twice as large as their primes. So their primes are not uninformative, I have to say. You can measure age of observation on this is real data, and this is the current standard, economic data. So I compare favorably, although we have only 2 data points, they have 50 each. But again, it's it's okay. It's a table we can compare with this if you want with all the results. I'm skip. We can measure this participant FAB. Similar to not so bad here, but receiving that's one force. So we do a lot of this but we don't lose the same. This is the group that I have no do it away a bit. There's correlation with all this parameters to compute, So these are the 3 parameters. This is the PK. So there's some correlation between the 2 P's of PK. There's some correlation. So this E, A, F, E, and LA are all correlated. But the E, F, E, and LA are not so strongly correlated to the power spectrum. There's no big. They are the most correlated one, which is not unexpected. Right? It's the most important part. So it's just a call on both of the correlations. But we can come back to the discussion because I have to go to part 2 of the talk, which is on standard killer velocities. So I don't know any more questions about the 3 power. Yes. So now that I got rid of PhD, I like this fantastic writer. So I can do this much faster because PhD was already so slow that we were months think there was a problem because not Cosmology where how maybe the thing is not correct. Now with this we use PTMC, which looks similar to but it's combination. So this is so bad that I very quickly know if I'm hitting the parameters or not. And then I plan to increase the KBs. But I think it's also interesting that I'm just going to analyze with epochs now. And they're not here to say, but I'm actually this PK, I developed from this PK leads. But they are all at ratio 0. So they are the same method. So they need to do one thing on the color where these are all together. And these are shared parameters, and it should be improved a lot. So now I can do these things.
So I have a question about the, so you go to effectively case of about 0.2, 0.3, this, right?
0.3.
And that's because the structure of the extra terms that you get are provisions you're getting from EFT, basically, right? So it's a question maybe not for you, maybe for some of the other people here, but isn't there kind of some symmetries, some structures that have to go through all orders? So in any perturbation theory about how okay you get in there. So it's not just 1 or 2 loops, it's just.
I will ask you to hold your question for the discussion because then we can discuss EFT and extended Galilean invariance, which is more or less what you're saying. And we tested this, but let's see for the discussion, otherwise it'll be too late. But this is true, you're right. No, we tested with this as well. And you're right, this is extended Galilean invariance has symmetries in it, and that's what you use in the end. This actually, if you want, is assuming lambda actually Einstein de Sitter for some of the internal calculations. And there was some criticism that you assume Einstein de Sitter somewhere inside of it. Although people always claim that dependency was not big, so we tried this, and we got similar results.
Can I question is, think any reason for not model we have, I don't think WA have not they call it parameterization. I mean, sorry, what you oh, as the question you're trying to address here is trying to diagnostic about it on, but also if you dig any crazy model, I think you're not looking at much also in those plots is very good even off plots.
So the more you make assumptions, the more you can increase your precision. That is for sure. That's the Bayesian way. But what you call crazy model not will depend on people. But you're right. You can do different models, and that's what this does. But what they say is that you can do this analysis, take the ENDs, and those are the data, and then you can use that to convert to any model you want. then you can go to another range of these guys, right? So I think this will allow you just to keep going if you want for a model dependent approach.
What I mean is that you're losing the factor two, right? So this is a lot in terms of where you get.
Yeah, but
Is it worth the price? Sure.
that is up to you, right? I'm giving you an alternative. Then, of course, I understand. I also do model dependent analysis all the time, right? You're right. But when you have tensions again, why do you gain a factor two? And then you go, there are two things which are 5 sigma parts. I really gain. So let me just, before I get too late, let me just skip to the, I'm going to be fast in the second part, okay? Because I want to go to the gradation later. I think people are more interested. But I just want to say that another thing you can do, and you can or not do the free power analysis, and this will not be free power now in first second. So is that you can, from supernovae and binary neutron stars and dark silence, you can get information which goes beyond just a distance indicator. You can do standard candle lensing. There are many people doing this. For redshifts above 0.4 or so, they start having some signature, but this is non-linear. It's hard to model. We have to do simulations. You can get peculiar velocity correlations of standard candles. This is quasi linear. This is easy, but it only goes to redshift 0.3, maybe 0.4 if you push a lot. And you can get extra information from that. So now I'm pushing towards the precision that he was saying. I can get more precision of the data. And then that's what was the difference to that Mane was asking. So what you can do is that if you go to free space, sorry, if not now you go to free space, but the process of supernovae are not random. They are correlated. So if one supernovae here is moving, you got affects probability of another supernovae nearby moving as well. So this is receding. There's an excess probability that nearby supernovae also will be receding from you, and vice versa. Right? So this information is encoded in a whole diagram residual and correlation of the error bar. So if you get the error bar and the residual, they are not just noise, they are correlated. Right? And in noise correlation, they actually reach farther than the next correlation, but there's one of the key term. But they have high reaching correlation, long reaching correlations. You can understand the mesh space, some noise space, and you can do phase spectra at least. By given, say, supernova, you can use them as density traces, velocity traces, or the cross spectra. And the interesting thing is that if you talk about the density part, you get this sort of simplify. You get this 1 plus beta squared that actually speaks distortion. Okay, and you get the bias of your object. Okay, but when you go to the velocity spectrum, there is no bias anymore. You feel the bias if you have velocity. And you have a bias. So you combine all three, you can break the difference between bias and sigma 8, for instance.
You're assuming here that the velocities are always like there's a projection operator, so they turn the vector into some scalar. There's still that velocity.
It's the rate of velocity. It's the rate of velocity. But there's no assumption. It's just what you measure. That's what affects the direction of and the distance.
I guess if you picture this EFT perspective, just that we did.
You're right. I'm just going to go fast to show you what you can do. So you can do this PVP, delta delta, delta V treatment to analysis with only supernovae. But of course, you can combine galaxies. Galaxies will be there. So then you can cross-compare the supernovae density traces and the galaxy density traces, doing a multi-trace analysis, including peculiar velocities. And then you can go to a 6-cycle point, which is GSS, which is gas, supernovae, gas, equal to density supernovae, the density supernovae, the velocity. And I'm just showing results for the two smallest thing and from 0.4 for LSSD, supernovae combined with I think it's a density, yes. So you get the normal full shape density result for sigma 8, for here's gamma, allowing the growth rates to have this free gamma property index, which is now different than 0.555 and 0.5 grams. But I'm going to show you the inclusion when we get number evidence. If we include now the supernovae velocities, you go for the blue to the magenta. If I also include the supernovae velocity, the density of the supernovae, I go for the magenta to the orange. And with the CMB one. So just by adding the supernovae, which will be there, well, string data is there, but I have an SSD. With the density of gas, you gain a factor of 2 or more in your figure bands.
How does this compare with the velocity reconstruction from the KSC?
Sorry.
Velocity reconstruction from the KSC.
You're talking about the KSC and
Companies probably assuming so yeah, so these are our forecasts. So this point here, I'm assuming 7,000 degree survey, which had 50% spectral completeness, which means it's a lot. On this area of the sky, you see 15% of spectral that explodes. So LSS can do that up to redshift 0.4. Should be doing more than that. When you push to here, it's already going to more area, more supernovae, and going to higher redshift. So this is probably too optimistic, but they should be low. Okay, the same just to show that this is very orthogonal to the same beam. Okay, of course, I had to talk about the star a bit. So you heard about all this about people fast, the gravitational wave part. There have been many talks already about this. The thing is, what I want to, the important thing to know is that the gravitational wave measures the absolute distance, where supernovae only measure relative distances. This is an important point. That's why supernovae themselves cannot measure H0 at all, where gravitational waves can. Now, you cannot measure redshift. I think Ricardo mentioned this very well. Of course, if you have an optical counterpart, as Claes was saying, then you have a standard candle. You have a pair Z and distance. That's a standard candle. Now, this is what you see when you're doing. I'm just showing the most basic waveform model, simplest at 1.5 pn and the phase 0 pn and amplitude, just to show you that this is how things kind of enter. So you have the mass, as you say, 5.6. Here you have the distance of the denominator. And you have the phase time. And there's no distance on the phase time, just to be clear. But you have the Chirp mass everywhere. So the Chirp mass is very well measured because of the 0 pn. This is what's measured in Chirp mass. And then 1 pn, you measure the symmetric mass ratio. At 1.5 pn, you start measuring the speeds. So there's a hierarchy that you measure very well the Chirp mass. Then you measure very well the symmetric mass ratio. Then you measure moderately well the speeds and the distances. That's why this is set at 20% or so whatever. They are down the hierarchy. They only enter the amplitude, not the phase, where there's lots of information. And the other important thing, if you never thought about this, is why all of a sudden we go from 100 objects to 200 to 100,000. And the reason is that gravitational the power is 1 over the power of distance, not just 1 over distance squared as supernovae, for instance. That's the most important thing. So if you prove a factor of 10 your sensitivity, you reach 10 times for the distance, 1,000 times more volume. Whereas for a telescope, you increase your area, you only increase by square root of area, the amount of photons that we have, the amount you solve, the magnetic field. So there'll be differences. I don't know, 2030, 40s, when, but there'll be differences. So this is like forecast for binary star for different signal to noise curve. Let's put 12. Then you see, yeah, these guys are redshift 1. And then the challenge is not finding them in the IC telescope, it's finding the kilonovae associated with these guys, which are very faint at redshift 1. So we did this analysis of, can we do this standard candle velocity that just show like a 692 point analysis with the drive size? How does it compare? So this work I did with Martin, this was Viviani and Alex Viviani, it was Bulldog. Of course, we have less symmetric supernovae in the sense 30, and you get more precise and low Z, but you have many fewer events and you are farther away in time. So let's show you just some results. I'm assuming here 5,000 binary stars, which nowadays seems a bit. I thought this would be 5 years. Now it's probably this would take 10 years. So probably at half than that, or third than that, because the rate has been remeasured. But this is what I get for the SCPGS, for sigma 8, H0, omega beta, including curvature here as well. I'm just taking now binary star distances with the follow-up from. They don't measure sigma 8 and gamma, if I just use the distance, but they measure H0 very well. As Claes was showing, or what Claes showing, omega beta and curvature. So it looks okay. But when I combine the distances with the 692 point analysis, I measure sigma 8 and gamma, which improve a bit, but not too much. But H0 goes from 2 to 0.08. I can improve by more than factor 10 H0 by combining the distances and the clustering. And also curvature, which improves by a factor of 10. Right? I can really pinpoint curvature by combining this 692-point analysis with. So these are the big things. This we don't do so well spectroscopy here. These are potential things. I'm going to skip this because I'm going to be more or less on time, and I have a third half of my talk. So let's talk about science as robust standard candles. Finish. So we heard today about the dark side method. You just, you can just correlate with science with the galaxies to find the redshift stochastically. For a line of sight sometimes, and this is work I've been doing with Josiel, and Tatiana, my student. And of course, as been discussed, now we have to worry about the completeness of the galaxy catalog. Right? This can be a problem. So some of your pilot black holes may not belong to any of the galaxies on your survey. Then you need some information about their population, to take into account this completeness. You have to, should measure the merger rate together with the cosmology principle. So these are difficulties for the line of sight method. The spectral science, Ricardo mentioned, I think yesterday, which you try to get features of a mass solution to refer cosmology that's also being proposed. We heard about peak science yesterday. I'm not going to repeat here, but it's a different way to get distances. And finally, the last thing I want to say that another thing nice you can do is when you have lots of this, let's say for big science or say from right science, then we're going to have three distances that we mentioned. There's a Lunardi distance that we can measure the spin up to an absolute intrinsic magnitude. You can measure the evident distance with the free power. I just told you that the free power gives you evident distance more independently. And you're going to have the gravitational distance, which we usually just call the Lunardi distance. But in modified gravity, the distance that enters the wave okay, this will be different than the Lunardi distance. And many modified gravity models where they are not the same. So sometimes you have this difference between the atom and the titanium. And people have proposed it's not so active field, but it can have something called cosmic capacity. You can lose some photons every now and then during the universe because maybe they just it does that is kind of simple to take into account. We have the branding, you can see that, but could be that's absorption, but you have models that propose that photons can decay to actions, for instance, when you have magnetic fields. So you can be losing some photons, principle, right? If you're losing some photons, sorry, I forgot 1 plus z squared here, but this guy is not different from the guy 1 plus z squared. You start to break the Telenor theorem. Now, we have the tools now to measure all this independently. Free power gives you the dimensionless and distance. Supernovae gives you lambda DL, where lambda has implicit magnitude of supernovae here. Right? Again, they only measure better the distance. As you know, what kind of latest, magnitude, let's say phase or whatever you prefer. And the gravitational wave measurement is big gravitational wave. So if you combine all three, sorry, I say that for free power, spinning gravitational waves. You can test all three, you can test with gravity. Okay, so this is what we did. Ricardo, Isabella. So this is I'm talking about 24. So there will be Roma will be finished. LSS will be finished. No. So I'm just saying that it's a crazy amount of sort of familiar spin because this is SSD after over 10 years. Right? So we did all that right science, now you can just take more spin you can do more follow-up spectroscopically. But this is a you can move this and below, this is already so many that you're not going to be there. So this is just a forecast we did in Roma with the Villanova of registration, and some of them are going to have GRBs. So again, this is 5,000. You can scale up in one. And if the error gets, okay, so spinning of course gets you a very tiny error in the distance if the losses are dominated. But this is not over again, because it doesn't matter. Then doesn't matter. You get the Roman supernova, maybe they go much deeper, but they have many less events. You have the kilonova, you have the GRBs, and you have this free power, which is the ring. So you can now combine you can do ratio of these things. You can do gravitational wave over LA, TL over LA, and these guys should be 1. If you give assumptions of low cosmic capacity, they go and find that it's true. And you can measure this eta, which is the ratio of velocity and diameter. You can measure this zeta, which is the ratio of radiation rate and angular diameter distance. And we can go to the discussion where you can measure this guy to 3%, this guy to 9%, and you can even measure the running of the dark mass. Because the running of the dark mass is what makes this radiation rate distance illusion out of this house. So you can do very interesting model-dependent things. Data become available. Of course, if there's no particle mass, which is what we usually do, you can improve your sensitivity more, and then you can measure this modified gravity now to 2% in different radiation beams using VW, LSS, and spinovic, which are beams, and you can do much better if they take a lot because they're being more, but if you only go radiation. You can also measure the running of the black mass, 2%, 10%, or 100%. Sorry, this is not 1%, this is 1. So the second part, but there are lots of things you can do which are model independent. I think the community will start taking this more seriously. And again, we did this in a way proof of concept real data analysis with few K beams and with false data only with getting, but we got a 2 sigma-ish low H of C, but this will be very promising with testing nucleic data. And in the bispectrum, which we did not use at the moment for the real data, will help a lot, maybe more precision. And gravitational science will also help us a lot because they are no longer only measuring distance. They can be used as tracers of velocity, of density. They can improve a lot by joint constraints. And you can do, very sophisticated, very agnostic tests where you allow modified gravity to be in each beam to be a free parameter, modified, quantum capacity to be different in every beam. There's some caveats there. I can go into the discussion, but I think this is a promising way to the next years. And I stop here.
Again, with the transition to the discussion. I don't understand. Suddenly, that's how treats you. The scale model. I don't understand because if you change code, many other layers, depends on how much matter you have, depends on what kind of revenue you have.
Right. So the real scale of the nonlinearity of the universe will depend on your model. You are correct. What I'm trying to say is that you don't need to know the model for the nonlinear scales. It just has to be there. And this thing pick up the scale blindly. It's what I'm saying. That your power spectrum, the real one in the universe, must have this. So when you're doing what I'm saying is take redshift 0, 0.3, 0.5, 0.1, you have to have a small change in the high K. But I don't need to know how it is. I don't need to put parameters for it. The data, depend on the data, but I don't have to model it. On my likelihood, I don't model it. I just have the data, and this is free. And just propagating how the parameters enter in K and mu, the model can pick up this implicitly. So you're right. This depends on the real universe, but I don't have to model it. I don't know if I've convinced you.
So we got thanks for the presentation. Maybe a really question about free power. So we're essentially being the linear power spectrum today. So you're letting the data tell you what does it want for the K at some specific. I imagine that the error bars in the PKs are pretty large.
Yes.
What would happen if, like, one of your beams would disagree with the best fit to the CDM model or something like that?
Yeah, I mean, you have to do joint analysis, right? One beam can be a fluctuation, but they can disagree. What I can do if I have all the beams is compute sigma 8. I just assume some spline And I didn't show you the sigma eight. So you get a 10% measure of sigma eight. Of course, in blood you get 1% measure. Okay? But this is the way it's a sub-statistic once that could show you that something is weird on a linear perspective. But we're very pleased to see that this came out kind of okay. Okay, but you can do many. You can think of. We didn't. This is a new thing. We haven't studied deeply. I have to say. But you can start taking games and say, well, maybe the small scales or the large scales, one of them is disagree more than the others, and there's a hit, and then this is the data. We didn't analyze it, and you're right. It's an interesting prospect doing what, for instance, what we did here, but I think it's too conservative. That's what I was trying to quickly say. That I was allowing the linear parameters to be different, differential between all they are the same, but equal zero. So maybe these guys can disagree, and you say that simplistic problem between the recipes. Right? This is what I will see, but I think this is too conservative. Right? I want to go joint analysis now. So choices you can do in the analysis. Sorry.
Yeah. I'm interrupting because
No, you know what I was saying.
To this, we do the usual mass spectrum analysis. This covariance there is very much accurate, especially if you're using such large bits. The bandwidth that you use is very large. So actually, this usually, if you calculate POV, the error there will be tiny because you're using there's a huge number of modes in there. But in this case, they are very tightly correlated. So how come? I mean,
but I don't think this is the data correlation. This is the parameter correlation. This is saying, I can change a bit this P and get a change of P, which is kind of compensating by changing this P and a change in this P.
and P. Just that.
No, but if you just do PNP with all these things, this structure will change. Now, this guy is correlated to that guy, and then this guy is correlated to this guy, and no, it's hard to separate completely PK from these guys. You can do the game and see. Okay. See what I mean? It's a high dimensional thing. But you're right. So what your question is, I don't think there's an outcome we need at all. I think we can do it. In the Fisher Bay design, we tried 12 and 20 bits and I think 40 bits. Well, they were sort of similar, but then you have lots of.
You might be underbidding at the low case, and
So I
this just be okay. Just
okay. I can say something the same at one time. So you see these guys. Yeah, there's a reason that they are not related. It's because these are prime dominated. Because these guys are wavelengths which are larger than my window. So these guys are super horizontal modes, but I have to include them, compute the high loops. So these are K very large. So I just say these are LSS and don't mess with them. You see what I mean? Because I have to have them in my analysis, unless they are they're kind of fixed to LSS here, because they are really outside of my box. So these guys, otherwise they wouldn't have correlation as well. But I don't trust them. Because I have to do the analysis, I have to integrate K, automate payments, and I have to say what I'm speaking here, okay, do the integral. I have to put something there. Put something there. Make the integral. I have to say what they are. I integrate from K equals 0 to something K equals 1. I have to put something. Maybe there's a clever way to do this better than this. I just picked up something here. But maybe you can let them free. So maybe they pick up some relativistic effects. They have to get about this fine. But again, we wanted to have this thing converged. So fix this guys. Maybe we can.
In the way the channel things, it's a nuisance, but it's the private dominated.
Yes. These two are private dominated. These are not.
How does it depend the nonlinear correction that you have on those two bins and the extrapolation that you do?
I don't think it depends. This is really big one. The first one is 0.00 step times 3.
And then on the extrapolation to the smaller scale that you refer to.
I don't think they matter much again.
Yeah, I mean, look at this box there. I mean, it's very uncorrelated.
They are privately. If I don't, they are somebody most, they are not constrained by whether they test it.
No, I understand those, but I was better like the extrapolation, those smaller K would have a bigger impact on the nonlinear terms of your classical space.
There's somebody that actually talking about these guys. You know?
Yeah, but I mentioned before, maybe I misunderstood. I think you have like those 8 pins go to Cairo people.
Yeah, you're right. The most coupled from the EFT, you do the integrals. I'm not the big expert. Again, my intuition is that these guys will not affect much these guys. What you see here is also this, right? You have EFT integrated. So you kind of see this kind of spread in gas, which is also related to this, I think. Not only the relation with parameters, have this, but these are particularly poorly measured because they have, right? That's what I think. Yeah. So if you want, I have 6 real parameters. Well, actually, yeah, and these actually, my constraints are coming from here because these are beyond 1. These are beyond 0.3. So I only use these guys in, let's say, this is the other ones that put me here. Sorry. So S is the counter. Sorry, S is the counter. No, the counter that was a synopsis too. S is the short noise prepared. That's why now I'm prepared for the short noise. And this is not there. It's not completely. I also put that back, but I don't think the short noise can be that crazy. But it's anything like the IR because you have more to about the IR estimate. IR is correct. So we are not in the bit here. I don't think in one of the plots I showed we had IR summation. Here I don't think I have IR summation in this, but it's essentially parameter constraint. But you need to be more you need more bits of the yes, that's right. I think a lot of these higher we should do it in an hour to double check, but on some of the podcasts I showed you this and try.
It's those terms. What's their problem?
How do I fix them? I don't. Right?
Terms.
Yeah. So they it was what we discussed before. They have a closed form of so C naught and C2 is related to the monopole and parapole. So they have a K-square dependence on both, and this has a mu-square dependence as well, right? And these are free parameters. So how they enter how they depend on K mu fits. It comes from the vector 3, but then there are 3 parameters left. Free, so yeah.
K squared.
They are summing the okay, right? Summing.
Well, so I mean the standard computer square is K squared okay. But you can
No, yeah. Okay, I understand what. Sorry, I understand what they are multiplying the linear perspective. Yes, yeah. Of course. I had it somewhere, but yeah, yes. I thought you were saying they didn't part it yet. They sum on the. They are summing them here, but the inside of that I didn't write, but they are pure linear. They are multiplying, and there's also the parameter center there. My 3 P's.
Does this depend on the choice? You have a maximum scale.
It's a good question. So in principle, it does. I'm doing at the moment. What I'm doing is exactly trying to investigate up to which scale I can trust this thing because this has not been done. For the shape, people do like blind model challenges to see you can put some cosmology to reconstruct it up to some K. What people have done in general is 6.3, but I tested it at different K masses. Didn't change too much. 0.25 didn't change too much. But if you push, I didn't push higher than 0.3. So, but I tested lower than 0.3 to see if the tension disappeared. It doesn't.
So two element choice, isn't it?
No, it does. It does because there's an assumption that you can do one loop up to a certain scale. Right? And the more you push, the more you make an assumption. Let's say, strong is the higher the max, the stronger is the assumption that there is no 2-loop correction at 0.3. That's my assumption. If I say there's no 2-loop correction at 0.4, it's a stronger assumption, but there's much more data and you get starter constraints. So in principle, you should do what you should do is do some tests of simulations to see this. And then it's no longer a choice. You say, and this is what people do. You say, I have put some few cosmologies which look very different, right? And then I reconstruct it. Do I get them right, or do I get a bias? If I get a bias, I cannot use those scales, and I keep going down until I don't get the bias. That's what I think.
that if we try shape it and models that extend basically the other machines formalism to capture some information from the shape.
So I get this question often. I mean, shape. What about shape fit? What about shape fit? So I'm not a big expert in shape fit as well, right? But the idea is that you have a set of templates, which are kind of chosen in a way which is agnostic, and you kind of leave it free. But then the analysis did not use a shape fit analysis. I don't know why exactly.
Because projection, that's your
What?
projection. That's
So the full volume, prior volume effects kind of things. Okay, so that's one thing. Although this, but the point is, I think shape fit is a nice idea, but I think this is more fundamental. And I think, of course, I'm very biased. I have B1, B2, B3, B4, B5 on this. But I think it's more fundamental because you understand what's going on exactly. The shape fit is you just run it blindly. But maybe someone can defend shape fit better than this. I don't know. I like it. It's going on the same. Let's put this. We have similar goals of trying to remove the model dependence of the power spectra. It's just different ways to reach that.
Yeah, but I mean, the big goal, like doing cosmology, I don't know. You cannot extend this to spectrum. You need to try to
The shape fit for this.
Sure.
Okay. So B6. Second 6 bias. So I don't know. Yeah. I like the shape fit, I discussed a bit with Hector at some point this. I think he was a referee on one of these papers I showed, but anyway.
Sorry, maybe I can ask later, but can you say something about those 6 times to? I mean, can you do something more? I mean,
For the gravitational wave,
yes.
something more. So something more. Well, I'm waiting for the end of the question. You have something in mind usually when people say this.
No,
I don't know. These are just results. I don't know where it should go. What do you mean something more? So I mean, I think the point I want to make here is that this is the one I want to look at. Okay, this is 2000. So they are very sparse. Imagine doing a dancing analysis with 5,000 galaxies. Whatever. But what I'm showing is that even 5,000 is very low number because it has brings lots of degeneracies. You still gain concentrating power. This is not the one there, but you still gain concentrating power. So I think the point is, probably should be traces. Now you can do something with big science, which that's simpler. Velocity, big science, didn't think of these things. But the velocity part really, so there's two things. The velocity part is really different, depends on the device, it takes lots of the chance. This first. But then you say, wow, then it's straight off, they make more than, right? But they don't have H naught, right? There's no H naught, So you can do some same basic everything, but you've got in, but the separate that methods, So each time you can do that. But this gets you H naught. So you also raise the chance with H naught helps, even though they're very slow objects. So I think that's the big message. Now you can do more. Yeah. You can do lensing of this guy, really do, but especially do by the pole, they should have put lensing signature of the high pressure. But not the message.
But to be really nice the velocities to the accuracy you require.
This is okay. We can revise this with the US GW Dali code and whenever finish it. But this is assuming, so I'm assuming some error for the distance, which is not too different.
I mean, you're using the velocities,
but okay. So the error of the velocity, the error of the distance, directly related to the error is because the velocity is just it goes to the residual level diagram. Right? So the scatter is very the scatter of the distance. This is the direct. And then you have another count effect, you have a short line stuff, right? So this is comparable to supernova, not much better than supernova. But again, this is negative, what I call lambda, the other one, but here, well, so no. I think what we can do that is really try to, and it's what thinking is that using all the dark science to these things. And this was all here was on right size.
Probabilmente questi una e resistir fondamentalmente schizzare i livelli dello spedone.
Because the air comes from the other distance, so it affects imagine the spinning. Now, I'm assuming I follow up with the spinning. That's the thing. Okay. Otherwise, but if you don't, the airship is not a killer. It's that you can have someone will say, don't back with the spinning, you're gonna have difficulty separating what's like one from what's not. Because the air is for a single spinning, it's around 15 magnets. The red air, the photo C is 0.02. You put the Hell diagram, still dominated with by the distance error. But now you're gonna have lots of contaminants, and you cannot trust it no type 1A spinning, and that's becomes the big problem. Yeah, don't have the spectrum, then that's an issue, right?
That's, yes, I think, you know, only was better.
Right.
Well, they did a 2%.
Contamination. Yes. So people have been pushing this. I played a bit about this as well. You can do, but this 2%, I don't know this 2% contamination, how much would break this map? That's what I'm trying to say. So I'm not saying you cannot do it. I'm just saying I didn't assume this, so I didn't have to worry about this. No, the one not going to follow. They have almost thing is going to follow a fraction of this event. And again, I remind you, I said this was 24 months. So we have 50 years to follow up. And if you put the S3 to follow up, I don't know. No, maybe it's a better way to do it really. But you're right, if you don't, then you're right, to see that worry about this. This has solutions that you have to put the answer. But maybe Gabriel, I want to come for this has become a live discussion. No, but it's probably I to share the floor. You overflow to the discussion, and now you don't need 1 hour, right?
Right. Yesterday we had a break before the discussion. I think it was a bad idea. That's all discussion.
I think also, I think cutting off talks at an hour is also valid. Like, they can spend it 1 hour, but I can keep talking about what I. I am on Zoom, it's just that this is still sharing screen, and you can't have 2 people sharing screen.
Yeah, let's ask.
Yeah, there you go. Stop sharing. And now you have a question. We make you co-host. Are you? Can you share a little? No, we would have to make you co-host. Like 3 points.